constant. Remember that we, in the assumptions, we said x is non-stochastic, is fixed, and k is defined by x and also x squared. So it's non-stochastic and is we can treat it as a constant. And from this we see that beta 2 is a linear function of y. In fact, it's the arithmetic average of y using k as weight. We could write this stuff. Let's assume there are three periods or three observations. We could say our beta 2 is something as k1 y1 plus k2 y2 plus k3 y3. Just trying to expand that, and we see that beta 2 is a linear. It's just a linear representation, linear function of y. So with this, we've proved the linearity property. Next, we'll be looking at the unbiasedness. Hello, I'm Emmanuel. Welcome back to Emoji Economics. Okay, so next we'll be proving the unbiasedness property, and we recall we defined k as x over summation x squared. So now we'll be deriving this summation k squared, summation k big X, because we're making use of the values we gave there while proving this property. Okay, so first let's try to define what summation k subscript I is. Recall k is this. Okay, so that means summation ki will be sort of big summation on this, which we can write as summation this over summation x squared. And remember we said earlier that summation x is 0, the small x represents deviation from the mean. So if this guy is 0, then our summation ki is 0. So this is 0, right? So up next, let's work on summation k squared. Summation k squared. Our k again is this. Okay. Then we are squaring it first. And if we square this, this will be, this is taking a squared, while this is taking a squared. Then we introduce a summation, which is summation xi squared over summation xi squared all squared. And with this can cut one of the summation xi squared here, and we'll be left with summation ki squared as 1 over summation xi squared. Okay, and finally summation kix. Summation kix. Okay. Before we define this, let me try to work out one that is easier. Summation ki small x. Now we're working with small x. I recall our small x is capital X minus the mean, right? So this is summation ki, this minus this. And if we expand this summation kixi minus ki mean, right? And if we walk through this, we'll be having summation kixi minus x bar summation ki. Okay, so this will be summation kixi minus x bar summation k is 0. So that means our summation kixi is actually the same thing as summation ki big xi. So what we are trying to solve here, the big one, is exactly the same thing as summation ki xi. Okay. And to solve this, we bring in the value of our k. Our k is x over summation x squared. So we put that in here, x over summation x squared. Now is k times small xi. So this time this takes on the squared. We have the summation here, right? Which you can write as summation xi squared over summation xi squared. And we see that our summation ki xi is 1. Okay, so already deriving an expression for this, we'll be able to easily walk through our unbiased. Okay, so proving the unbiasedness property, recall we said beta 2 is a linear function of the dependent variable y with k serving as weight, so sort of like an average. And recall that yi, the stochastic specification of the population regression function, is beta 1 plus beta 2 xi plus mu. Actually, where we are working towards with this unbiasedness property, that we are trying to prove that the expected value of beta 2 is equal to the true beta 2. That's the goal here. We're trying to prove this. So putting the value of y in here, estimated beta 2 will be summation ki beta 1 plus beta 2 xi plus this, and this will be summation ki beta 1 plus ki beta 2 xi plus ki plus, and if we open this up, beta 1 is a constant, so we'll be having beta 1 summation ki plus beta 2 summation ki xi plus summation ki mu I. Right. Okay, and this is where these expressions come in. Our summation ki is 0, summation ki xi is 1. Okay, we make use of that last one subsequently. So putting in those values, this is beta 1 0 plus beta 2 1 plus this, and here we'll be seeing that beta 2 is estimated beta 2 is the true beta 2 plus summation ki mu I. Okay, so working with this, we'll try to take expectation of both sides. Remember, this is where we are working towards. So we're taking expectation of both sides. Expectation of the estimated beta 2 now will be the expectation of this, and the expectation of this side is simply this. This is a constant. The expectation of 2 is 2, right? Plus the expectation of this. So expectation of beta 2 is equal to beta 2 plus. Remember I said ki is non-stochastic. It's non-stochastic, so we can treat it as a constant and write it such that summation ki expectation of I. Okay, and from the assumptions of the classical linear regression model, we know that summation of this is 0 of mu, the expected value of your residuals, of your error term, of your noise term is 0. So if that is the expected value of beta 2, will simply be this plus summation ki 0, which is automatically 0. So with this, we've proved the unbiasedness property. Okay, finally we consider the minimum variance property. Recall that we defined that beta 2 from the OLS estimator as this summation ki yi, where k is x over summation x squared. Now let's picture another estimator let's assume beta 2 star and that estimator, and now let's assume this estimator has weights W, so not K. We're not trying to impose that W is equal to K and W is this. Let's just assume this. We'll try to derive the variance for this and we'll try to see where it is minimized. So assume that this estimator is given as this. Let's take the expectation of both sides, the mean of both sides. The expected value of our new beta 2 estimator will be the expected value of this, right? And similar to how we treated the previous case, Wi is non-stochastic and we can write that as summation W expectation of Yi. So expectation of beta 2 star is summation Wi. Expectation of Yi is your population regression function. But now it's expectation, so we are not putting the residual term there because we are looking at a sort of deterministic, the exact average which you can get using your population regression function, and this is simply defined as beta 1 plus beta 2x. Okay, so working with this, expectation of this is equal to summation Wi beta 1 plus so beta 1 is a constant, so it can come out. Same here, so beta 2 is a constant summation of xi. Okay, so for this particular estimator, for it to be unbiased, is linear already. For it to be unbiased, it means that summation Wi should be 0 and summation Wixi should be 1. If this guy is 0 and this is 1, then we'll be having the expectation of this as 0 beta 2. So we've shown that it's unbiased. It's only unbiased when summation Wi is 0 and summation Wxi is 1. So now assuming another estimator that is linear and unbiased, we want to actually see if the OLS estimator gives the minimum variance, and that will be doing in a while. Okay, so I'm going to take a break here. Let me clean this guy. Okay, so we walk through the variance now and see where it is actually minimized. The variance of this new estimator for beta 2 will be the variance of summation this beta 2, so we're just substituting it here. And from linear combination of random variables, we know that the variance of this is simply summation Wi squared. The term that's like a constant, we take the square times the variance of the actual variable, that's sort of stochastic. And we also know from the assumptions we looked at earlier, the classical linear regression model, we know that the variance of our y variable is the same as the variance of the residual, and this is usually depicted as sigma squared. So the variance of our new estimator beta 2 star will simply be summation this squared, and we can write that as, because this is a constant, summation of beta squared variance of beta 2. Okay, so then we just want to do some little mathematical manipulation. So if I rewrite this exact equation as this, so I write it as this summation Now I say wi minus xi over summation xi squared. Now this k, I'm just putting in the value there. I'm bringing minus this, and then I'm adding it back. No. Summation, the variance of beta 2, let me take that again, is sigma square summation wi minus this plus this. So it's still wi squared. We've not changed the form of this, we just introduced that's just driving our point. Okay, then let's now assume I do something like this. Probably I change these brackets, change it to big one. Okay, so we still have the same thing. And using binomial expansion, we know that if you have something like a plus b squared, it's simply a squared plus b squared, right, plus 2ab. So we do the same thing here. This is sigma squared, and we are squaring this plus this squared. So this will be sigma this squared plus, let me just expand straight away, plus sigma squared summation this squared. And now if we are squaring this is something like squared, okay, plus 2, and sigma squared is coming 2ab, so 2 this times this summation. Okay, so walking through, if I just try to rewrite this this formula, we'll see that, let me just bring this summation up here. Okay. We see that what we have here is just what we have here, but this is just squared. So if we try to simplify this formula, our variance of beta 2 will simply be this summation w minus xi plus sigma squared. Now this will take one of the summation x squared on the denominator, so we'll be left with this 1 over plus this. Let me write it again. Okay, so this is the variance. The goal is to minimize this variance, and we see that this variance can only be minimized when w is actually the value of our k. When wi is this over summation xi squared. If this happens, we see that this minus this will become 0, and so the value is already 0. And the same thing, I didn't want to write this again, the same thing, once this is xi over summation xi squared, this also becomes 0, and you will just be left with sigma squared over summation xi squared. So you see that when the weights used in this estimator is exactly the same weight we used in using our OLS estimator, the variance of beta 2 will be, this becomes 0, we'll just be left with this sigma squared over summation xi squared which is exactly the same as the variance or our OLS estimators normally. So what we are saying here is that for the variance of your estimates for your either for beta 2 or beta 1, for it to be minimized, we have to make use of the same weight used in OLS. So OLS pretty well just has these properties that are desirable: the linearity property, the unbiasedness property, and the minimum variance property. So with this, we'll be able to show that OLS estimators, given that the assumptions of the classical linear regression model are all satisfied, the OLS estimators yield the estimate with minimum variance in among the class of other linear unbiased estimators. Okay, so that brings us to the end of our discussion of the statistical properties of OLS estimators. Do like this video, and if you've not subscribe to this channel, and also turn on the notification bell to get updates of future videos. Your comments are also appreciated. Do also leave them in the comment box, and see you next time.
Hope you enjoyed the video you just saw. If you want more of our videos, please make sure you subscribe to the channel and click on the notification bell. Now, there is a way to enjoy to make the best of our YouTube channel, which is to go to the playlist section of every video or of every topic. So what you have to do is just type Economics on YouTube. When the page displays, make sure you subscribe. A bell button appears immediately, so you click on that bell button. Then go to the playlist section. So you're going to see videos, playlists, description, and all of that. So just go to the playlist section, and whatever topic you are looking for, look for the playlist and click on the video. Now, our playlists have the classes arranged in a very chronological manner. So if you want to see a class on ISLM, so it starts from the beginning, the simple ones, to the difficult to the complex ones. So if you want to see a video on, let's say, elasticity of demand, so you start from what is price elasticity, so from there then to the basic ones, and on and on. So I'm just telling you that in case you really want to make the best of this YouTube channel. And there's also one thing that I want to add, which is that our YouTube classes may not be enough for you. You may want a regular interaction with the tutors and all of that. So what you just have to do is to check the description of the video. You are going to find a WhatsApp link. So, but before you do that, I really have to tell you that clicking that link is going to lead you to one of our schools. It's going to lead to some of our schools. So we have MOGE School of Economics on WhatsApp, and we make use of our YouTube channel to run the groups. So the classes are paid for, so you're meant to pay for them. So to join our Econometrics school, so that is 2,500 naira per month, and to join our Microeconomics or Macroeconomics schools, so that is 2,000 naira per month. We also have we don't have schools of mathematical economics, because Microeconomics has its mathematical aspects as well as macroeconomics. So the mathematical aspect of macroeconomics is treated in the macroeconomics school, and the mathematical aspect of microeconomics is treated with the microeconomics school as well. So I'll see you next time. Thank you very much for watching.